We have learned how to find a determinant. I wanted to point out a couple of properties that a determinant is going to have. The first is that if you are multiplying matrices together and you want to find the determinant of the answer, you can actually take the determinant of each one separately and multiply those two determinants together. So it's going to be useful in certain proofs in mathematics. The next one is the determinant of a matrix and the determinant of a transpose are always the same answer. This is just showing you that it doesn't really matter whether rows are rows or columns are columns. You can switch them around and you're still going to get the same determinant here. The next one's a little tricky, so let me kind of give an example here. Let's suppose I take A as 1, 2, 3, 4. Then the determinant of that matrix, 1 times 4 minus 2 times 3, is negative 2. Now if I were to multiply the whole matrix times 5, that would be 1 times 5, 2 times 5, 3 times 5, 4 times 5. We're going to get 5, 10, 15, 20. You might think that when I take the determinant of that, I'm just going to get 5 times the original one, but that's actually not going to be true. As you see here, I'm actually going to get 25 times the original determinant. And the reason why it's 25 is because it's 5 squared times the original determinant. So you take whatever number you're multiplying by, and you raise it to the size of the matrix. So since this is a 2 by 2 matrix, that's why I got 5 squared. If it had been a 3 by 3 matrix, I would have had to multiply by 5 cubed. So it's a little tricky property, but when it can be used, it can really save a lot of time. The next property is inverses here. It's kind of useful that if you want to find the determinant of the inverse of a matrix, it's actually just going to be the reciprocal of the original determinant. And this kind of goes along with how that you need the determinant to be non-zero in order to have an inverse, because if your determinant was 0, you'd be dividing by 0 here. That would be undefined, and so then you know there is no inverse matrix. Regardless, these are just some fun little properties that are occasionally useful. And this last one here, it's a really neat property, but a lot of the time it's actually more work than it's useful for. In fact, it makes the problem harder. But there is an occasional 1 in 100 problem that Cramer's rule is actually the best way to solve it, and so it's good to actually see it. But I will say that even students that I've taught it to, rarely does anyone actually use it. But whenever I see, like occasionally one student will use it once in a blue moon, it ends up working out really well for them. So again, it's a good thing to know, but it's not that great, to be honest. So here's how it's going to work. We are going to calculate 3 determinants. The first determinant is based on the coefficient matrix. So, determinant here. So, we just look at the coefficient matrix, take our determinant, 2 times 4 minus 3 times 3. We're going to get negative 1. Then what we're going to do is we're going to take the same matrix, but instead of the numbers in front of x, we're going to take the right-hand side numbers and replace them. This would be 7 times 4 minus 3 times 11. And then the third one is we're going to take the same matrix, but instead of the y numbers here, we're going to replace those with the right-hand side. 2 times 11 minus 3 times 7. And I'm going to call this original one A for the initial coefficient matrix. I'm going to call the next one AX, and the third one AY, because I replaced the X's in the AX, and I replaced the Y's in the AY. And then it turns out the answer for X in the equation is going to be you divide the AX by the original one, so the value for X is 5. And if you want to find the value for Y, you take the Y1 divided by the original, you get -1, there's the value for Y. And so this is another way to find the solution to system equation where you don't need to do any elimination, no Gaussian elimination, no Gauss-Jordan elimination. This also lets you find, let's say, if you only want to know what one variable is but not all of them, you could use this just for that one there. The only problem is that in order to find these, we need to find all these determinants. And determinants usually take more effort than just doing elimination in the first place, so they're not necessarily better. Regardless, this can be useful. The main times I see this actually being useful is when you have your coefficients are actually letters, and if you want to find x and y in terms of a, b, c, d, e, f, then Cramer's rule can get to that answer without trying to play around. Because imagine trying to do Gaussian elimination where everything was a letter. It would be a gigantic pain. So that's the one time where Cramer's rule, I'd say, is really you want to use that. But otherwise, it's kind of just an optional method, and if you want to use it, go for it.